Right, so today we're looking at exercise 10, and according to that previous video I made about fractions, simplifying algebraic fractions, we see that we've got a little bit more challenging questions from in M to Y. So basically the first thing we see was we dealt with the issue of not cancelling. When we are supposed to simplify algebraic fractions, we can't go ahead and do something like cancel the 2 there with a 2 there, or that x with one of the x's there, or say 6 goes into itself once into 24 4 times. None of that can occur here because rightfully we have terms that are separated by a positive sign or a negative sign, and as long as those signs are present, we need to tread with care. So I'm going to make a brief list, just to like a checkpoint list, just to look at what we can do in order to help ourselves moving forward. So when we see fractions, let's just think about that. When we see fractions, we must think, number one, don't cancel. Let's do that. Don't cancel. Number two, separate. And then number three, that separation depends on whether we could or could not simplify. So first, let's just check numerator. Like terms, then we know we may add or subtract, but unlike terms will remain. So let's just look at, for example, number M. So we have 4x to the power of 4 plus 12x to the power of 4 divided by 8x. So let's do the check. We know we've got a fraction. Great. So fractions, yes, got it. Don't cancel. Right, let's just stop and say, hey, I can't do that. I can't do that. Not allowed. Right, so what should I do? We must separate. Okay, but can I perhaps check if I can simplify the numerator? How am I allowed to simplify the numerator? I look for like terms. Now, also what we can see from our past assessment is that we are only allowed to add and subtract when the variable and its exponent is exactly the same, meaning like terms are determined by the variable and the exponent, not by the coefficient. The variable and the exponent, if they are identical, then we use the coefficient to either add or subtract and simplify, which then leads us to our next step. Yes, they are like, so I may add. And 4x to the power of 4 plus 12x to the power of 4 becomes 16. X to the power of 4. We don't do anything to the power. So that power of 4 remains the same. The only time we change powers, we only change powers when we multiply or divide bases. Those bases depend on the variables carrying the power. So here, no timesing, no dividing. We are only dividing now in our next step, and this is when the power will change, because what I have here, I'm going to expand this in a way that just breaks it up slightly further. So what I have is, I actually have 2 to the power of 4. That's the 16. And then I have x times x times x times x. I could have done it for the 2 as well, but I'm focusing on the variable. And then I have 2 to the power of 3, which is actually 8, and an x. So what I am doing now is I'm cancelling. I'm saying, okay, if 2 to the power of 3 is at the bottom, 2 to the power of 4 is at the top, then actually let me just write it out to show exactly what happens in that case. Then let's do 1, 2, 3, 4. There's the 4 2's that gives me 16. 1, 2, 3. There's the 3 2's that makes 8, and then the x. Then let's cancel. For that one, I cancel that. For that one, that one, that one, that one. Right, no more 2's to cancel. Now I cancel my x. There's one, there's one. And what do I have left? I have 2 and then x times x, which shows me through that step that this that I have now I can go ahead and simplify because I have one term, number 1. 8 goes into itself once. 8 goes into 16 twice. And remember we said that we need to be able to differentiate the numerator from the denominator, which means that 2 does not go into the denominator but into the numerator. And then I've got my little placeholder. Now I've got x to the power of 1 down here, x to the power of 4, which I could see here left me with 1, 2, 3, x to the power of 3. So I don't actually have to write this one here. I do encourage it for now because we do get confused as to where to place the remaining coefficient and variable, for example. So it's a good way just to keep a position open and to make the position clear. But this that we have here, it's an expanded version of what we have there. So if we look at what we did there, we did apply our rules with regards to powers, and those only come in when we multiply and divide with a basis. When we add and subtract like terms, we don't change the powers at all. So now let me look at letter O. Let's do number O. Minus 9x to the power of 7 plus 27x to the power of 5 over 3x to the power of 4. And my first step, like we said earlier, let's check. What can I do first? I need to check, is it a fraction? Yes, it's a fraction. So I should not go ahead and cancel anything, but can I perhaps simplify? Can I simplify my numerator? Then I have to check whether my variable and my exponent is the same. And I see no. The exponents are not the same. The variables are the same, but the exponents are different. Therefore, these terms are unlike. So unlike terms cannot be added because their powers are not the same for the variables, which makes them different. So now I go straight to separating these terms. I can only simplify it when I've separated it. I keep my minus 9 x to the power of 7 over 3 x to the power of 4. And then as I separate my term, I check the sign. I have a positive, and this is also a little positive, but at the same time I'm checking, does a positive divided by a positive give me a positive? And yes, I could go ahead, it does in fact give me a positive. And then I go straight into my remaining coefficient, the variable and exponent. Right, now I'm at that point now where I can once again recall my little checklist that we used in our previous videos, and that would be using our sign, our variable, all of those. So once we've got that checklist, it's the go-to every single time. So definitely the sign, the coefficient, the variable, and the exponent. These are our important factors that will result in accurate work. A negative divided by a positive, this is the division sign, leaves me with a negative. 9 divided by 3 leaves me with 3. And I made a clear distinction between my numerator and my denominator to work accurately. I have a little placeholder here because 3 divided by 3 is 1. 9 divided by 3 is 3. Now I've got x to the power of 4. It moves up and it becomes x to the power of 7 minus 4, which becomes x to the power of 3. And then I've got my positive sign, which remains positive because I've already sorted out the sign here. 27 divided by 3. So I say, okay, cool. I've got my little placeholder. 3 goes into itself once. 27 divided by 3, 9. Now I've got x to the power of 5 at the top, but I'm taking that x to the power of 4 up. And I see x to the power of 5 minus the 4 in the power gives me x to the power of little 1. So what I actually have here is negative 3x to the power of 3 plus 9x. And because they both stand over 1, I don't have to still write anything in the denominator. It's just a placeholder to make sure that I leave my values in the correct position. Right. Now that we've seen one where we could not perhaps simplify that numerator before continuing, we want to then see how are we going to apply this rule when we have something like number p. A little bit more work is required here with regards to our rules with exponents. So if we look at that one, once again I can see, yes, I have a fraction. This is an algebraic fraction. I'm not allowed to cancel unless I've simplified first. So let's do that. 15w to the power of 3. Any letter of the alphabet may be used as the variable. 18w to the power of 8 over. In the bracket, a negative 3w to the power of 2. Close the bracket to the power of 2. And I see now, okay, I first need to check what is going on here. And this is when our rules of BODMAS also still play a role. BODMAS is so important because BODMAS reminds us that brackets take priority, brackets together with product. And this actually is product right here because we know this is a shorter version of writing minus 3w to the power of 2 times another minus 3w to the power of 2. Once I've already assessed my numerator, I can see, okay, great, these are not like terms, so I will not subtract. But let me now first look at my denominator. My denominator needs to be simplified now. So if I still leave my numerator and denominator in its place, I'll work accurately once again, and I look at negative 3 to the power of 2 gives me a positive 9. W to the power of 2, which is then still to the power of 2, becomes W to the power of 5. So I've already now simplified the denominator. I leave the numerator as it is. It cannot be subtracted as the powers are not the same. Let's check if I wrote that down correctly. Yes. Then I go straight into separating my term. And then I go straight into checking out this sign. And I see, okay, this is a negative, but there's a little positive, and I want to sort it out right now before I go any further. Negative divided by a positive is a negative. And then I still write my 18w to the power of 8 over 9w to the power of 4. And here I see that I can, in fact, go ahead and simplify now. So once we get to this point where we have one term minus one term, because we learned that product and division, quotient, product, these two operations create one term. Then I can go ahead and now I can simplify. So I can look at terms that are going to be a simplified version of what I started with. And this is the basis of equivalent fractions. Equivalent fractions were those things that if I know 2 over 3 is the same as 4 over 6, it's because I simplified or I manipulated using a factor in the numerator and the denominator that allowed this technique. So let's go back to 15w to the power of 3, and I will simplify this fraction using a factor of 3. Immediately I put my little division line down, because I don't want to make any mistakes. And I go straight into saying, what can go into 9 that can go into 15, and that's 3. 9 divided by 3 is 3. 15 divided by 3 is 5. W, now I look at where my power is higher, and I see 1 remaining in the denominator. Now I've got my negative here. Yes, don't lose it. And then I see, okay, great. What have I got in my next step? 18 and 9. 9 goes into itself once. 18 divided by 9 is twice. So just put your little placeholder there. 18 divided by 9 is in fact 2. And then I've got my w to the power of 8. Where is the highest power? It is situated in the numerator in this case. Therefore, w will remain in the numerator with a power of 8 minus this 4. W to the power of 4. And my final answer, very important here, my final answer is going to look slightly different than some of these other ones that I've done. I want to just quickly move this. And very important that we just work very carefully when we have something like this. So I've just moved this one up here so that I can have a little bit more space to work. And now my final touch is to write the final answer in terms of 5 over 3w minus 2w to the power of 4. Let's check. These are not like terms. Like terms may only be added or subtracted if the variable and the power is identical. Like terms may be added and subtracted when coefficients are different. The coefficients do not determine whether it's a like term. The like term is determined by the variable and its exponent. Right, so very, very complicated if we do not keep track of what is like and what is not like terms. So we always need to work accurately when it comes to using those terms correctly. And the last one I'm going to do is number y, letter y. Just because I see something that I've now explained in my previous video that will be uploaded soon today, that concept of using our distributive law when we have a coefficient of a bracket. This is something that seems to cause some confusion. So let's just get a little bit more familiar with this. Here is my coefficient of this bracket, basically a product multiplied by a product. In my bracket, I see 1, 2, 3 terms, but this is not strictly a coefficient that will remain the same. The 3 multiplied by the 4 will create a new coefficient. My variables will however have to follow the rules of exponents. And this is the only time when exponents change, when we have product or division. This process that's been indicated using this arrow is a process called the Distributive Law. And my previous video will explain this in detail. If I distribute this monomial into this bracket with 3 terms, I have to have a result of 3 terms. I can't have a monomial out of a trinomial, only if I've simplified it afterwards. So let's do this. I'm going to take all my brackets back now, and I'm going to individually times them in as I go one by one. I'm going to have my checklist here: sign, coefficient, variable, and exponent. Here's our checklist. Tick them off one by one as we go ahead. 3 times 4, that's a positive. Sign is positive. 3 times 4, 12. M to the power of 1 times m to the power of 2, m to the power of 3. N to the power of 1 times n to the power of 3, n to the power of 4. Back to my 3. Next term. Positive times a negative is a negative. 3 times 8 is 24. M to the power of 4, n to the power of 3. Let's go back one step. 3, that whole 3n now needs to be multiplied by the third term in the bracket. And I see, okay, I've got a positive times a negative is a negative. 3 times 12 is 36. M to the power of 1 times m squared is m to the power of 3. N times n squared is n to the power of 3. There are no like terms here. We can't fuse things together when the variable and the exponent is not identical. Right, I'm done. Now I go to my denominator and I see, okay, great. That 3 is in front of the bracket. Mn to the power of 2 becomes m squared n squared. Plus, now, what is different with this second term in my denominator is the fact that this whole 3mn is squared, which gives me positive 9 m squared n squared. And look at that. M squared n squared, m squared n squared. The coefficient does not have to be the same, but the variable and exponent has to be the same. Therefore, I may add what is in my denominator, and that's simply 3 plus 9 gives me a 12. M to the power of 2, n to the power of 2. Let me check what I have in my numerator, 12. M to the power of 3, n to the power of 4, minus 24. M to the power of 4, n to the power of 3, minus 36. M to the power of 3, n to the power of 3. Not done yet. We are not allowed to simplify anything up here because they are not like terms. Separate them now. Now we go back to what we had to do here. We are going back to our little checklist. Here's my checklist. Is it a fraction? Yes, it is. Don't cancel. Let's just stop there. Don't cancel. First separate. First separate. Right, let's get that out of the way. 12. M to the power of 3, n to the power of 4, divided by 12, m to the power of 2, n to the power of 2. Minus, because here I see a minus divided by my little positive at the bottom gives me a negative. I'm left with 24, m to the power of 4, n to the power of 3, divided by 12, m to the power of 2, n to the power of 2. That denominator remains the same denominator for every single term when we separate our numerator like this. And here again, just to check, we still have a minus here, as we had a minus there. and over 12 m to the power of 2, m to the power of 2. And now you may take your pencil. You may take your pencil and you may go and simply cross out whatever you find is in common. So I'm going to take a light color here, just a highlighter color, and I'm going to simply go ahead and get rid of values that I know may divide. That is my coefficients first. And then I'm going to look at my powers. And I'm going to see, okay, great, I've got m squared here. I'm going to have 1m left up there. I'm just doing this in a different way than the previous examples because you are allowed to. N squared there, and I'm going to have n to the power of 2 left. M squared here, I'm going to have m to the power of 2 left. N squared there, I'm going to have n to the power of 1. M squared down here, I'm going to have m to the power of 1 left. N squared down here, I'm going to have n to the power of 1. Let's jot that down. That's just 1. M to the power of 1, n to the power of 2, minus 2, m to the power of 2, n to the power of 1, minus 3, m to the power of 1, n to the power of 1. I don't have to write these ones. These are just there, even like this placeholder here. It's just there to help me. Now, is any term here identical to the next? Here's one term, there's one term, there's one term. No, my powers are not identical. So my final answer, mn squared minus 2m squared n minus 3mn. And if you want to take it one step further, because we're working with an alphabetical order, minus, this is optional, minus 2m squared n minus 3mn plus mn squared. That's very theoretical right now because we're descending the power of m because m takes priority. Alphabetically, it comes before m. N for Noddy, so m for Mommy before n, and we are writing it in a descending power of m, and this is usually what a trinomial will look like. But that's really just to neaten it up. And that should summarize all those really important aspects that's recapped in this exercise. So this is from Mind Action Series, exercise 10. I want to encourage every grade 8 learner to really just go through these crucial aspects. If it's a fraction, don't cancel. Separate the terms. You may only add or subtract a numerator or denominator when the terms are identical. Not coefficients. Coefficients do not determine like terms. What do in fact determine like terms? In my previous video, I said you may add an apple to an apple, but you may not add a banana to an apple unless you want to create new fruit. But maths is all about like terms. An apple, you may add an apple to an apple. You may add 3 apples to 4 apples, but it's the apple that determines what the like term is. The apple is the one that determines it. Therefore, the variable determines whether the term is the same and its exponent. The variable and its exponent. Right. So I hope that helps you guys out a little bit for today.